Welcome, everybody. We certainly appreciate you. A lot of people, I think, are coming back from past webinars. Today, as you can see, the subject is Boiler Basics, Design and Application Differences, and this was initiated because of numerous comments from our viewing audience who stated that our webinars, though they're informative and helpful, they might be even more so if we were to spend a little more time on the fundamentals of boilers, so that when we take specific dives into specific subjects, that they may be more clearly understood because of a better grasp of the basics. So that's what we'll attempt to accomplish today. We're going to review the basics, and though we are limited in time, give you at least what I think are the essentials. That said, what we will be covering today starts with the basic boiler manufacturing requirements, which then would lead us into what's included in a boiler package. And from here, we'll delve into the various types of boilers, which are most commonly used today. And then we'll be going into, this will kind of give us a 35,000-foot view, and then we'll dive into more detailed specifics of the industries served, including some application information. And then we'll also be covering the design construction of the boilers before understanding the load, which I think really is probably the most important thing for today as far as the takeaway is concerned. It's the stuff that I'll be covering at the end. So, starting with boiler manufacturing, one must understand and appreciate that boilers are really controlled bombs, which, if not properly understood and operated and maintained, can cause very serious damage, not only to the property, but human life as well. And for this reason, all of us manufacturers in this industry take inordinate care and pay close diligence in assuring the boilers that we manufacture not only contain high-grade materials, but also we follow the very rigorous standards as developed and outlined by the ASME, which is the American Society of Mechanical Engineers. Now, this code is very detailed in its instruction and essentially breaks down into two major sections, beginning with Section 1, covering steam and hot water boilers, which for steam boilers operate above 15 psi or 250 degrees Fahrenheit. And then for hot water boilers, above 160 pounds. Now, that's hydrostatic head, and or above 250 degrees again, which is the same as 15-pound steam saturated, that temperature. Now, these hot water boilers operating at these elevated pressures and temperatures would be considered what we call high-temperature hot water boilers, and would be built almost exactly like a high-pressure steam boiler, except for the differences in connections. Now, Section 4 is the next category, and covers those boilers operating below 15 pounds and 250 degrees, and those hot water boilers below 160 pounds hydrostatic pressure and 250 degrees. These are essentially heating boilers, though some low-pressure steamers can be used for light process applications as well. Now, I mentioned a bit ago that the ASME code is quite specific about how these boilers will be constructed. And as such, it will detail things like boiler plate thickness to be used, the type of welding to be applied, like a full penetration weld, when stress relieving is necessary, including the temperature and time requirement, when and what to x-ray, hydrostatic testing, and so on. So really quite specific. Also requiring an independent inspector be in the plant at all times to witness all the boiler construction, to assure the plant's quality procedures are not only properly followed, but also applied. Let's talk next about the general types of boilers we will be considering today, understanding that those shown on the screen represent the general categories into which all boilers will fall. They include the fire tube boiler, the water tube, the tubeless boiler, and the electric boiler. These, I have to stress, non-residential boilers in total will span a wide range of sizes from about 200,000 to 365 million BTU, and require, and I should say arrive at the job site as shippable packages. Now, that's a horsepower input range from about 6 boiler horsepower to almost 11,000 horsepower. And as mentioned, can be applied to a vast array of applications, which I will touch on when we cover more of the specifics of each boiler type. You'll notice I keep referring to boiler packages because that is what is commonly shipped to the job site. Years ago, let's say back in the early 20th century and up until about the mid-1930s, boilers arrived at the job in pieces, including a pressure vessel from one manufacturer, a burner from another, and controls from yet another manufacturer. And you can just imagine the finger pointing when things weren't going right. So, as mentioned, today we have complete boiler packages arriving at the site which the manufacturer takes full responsibility for and includes, as you can see, the pressure vessel, the burner, and the controls all pre-piped and wired to minimize installation time at the job. And I also wanted to mention the controls on these packages are broken down into 2 very specific categories, which are the burner management and the combustion control systems. Very simply, the burner management control system is supervising and controlling the burner sequence of operation along with its safeties, while the combustion control system is managing and controlling the fuel air settings, the burner modulation, feed water control, draft control if applied, and so on. But both of these systems are fully integrated and work seamlessly together. Looking now at the industries that we serve in this business, they can be broken down into 2 broad categories, commercial and industrial, with the commercial segment being primarily low pressure or hot water comfort heating, and the industrial typified by process load applications with the possibility of some comfort heating as well. And this is normally accomplished through a separate steam to hot water converter, such as a shell and tube heater. Starting now with the commercial segment, you can see the needs can be satisfied with an array of boiler types, including fire tubes, vertical tubeless boilers, electric boilers, water tube, cast iron, and copper fin boilers. Most of these will be built in accordance with Section 4 of the ASME Code for low pressure. The industrial segment is also steam and hot water applications, with the emphasis being on process steam, though some comfort heating can be included, and as I mentioned, is normally accomplished with a steam to water converter, such as a separate shell and tube heater, or it could be a plate and frame heat exchanger. As you can see, the boiler types are somewhat similar to the commercial products, though some commercial boiler products have been eliminated due to their inability to achieve higher design pressure, specifically the cast iron and the copper fin boilers. So in the end, in the industrial segment, we have fire tube boilers, both horizontal and vertical. Again, we have the vertical tubeless boiler. We have the electric, the water tube, both natural and forced circulation, and of course we have the large industrial water tubes, also known as IWTs. Now, for a closer look at these designs, and we'll start with the fire tube boiler. As you can see, it comes either in a horizontal or in a vertical orientation, and typically spans a package range between 15 and 2200 horsepower, with design pressures for steam between 15 and 250, and for hot water boilers between 30 and 160 pounds. This means this boiler can be used in both process and heating applications, and is typically found in industrial process applications such as food, petrochemical plants, hospitals, university campuses, and so on, wherever high pressure steam is required for either motive force or higher temperatures. You should also understand the horizontal fire tube boiler comes with either the dry back or the wet back design feature. The dry back fire tube, as you see now on the screen, can be either a 2-pass, 3-pass, or 4-pass design. This one that you're looking at, the cross-section, is a 4-pass, and it includes a refractory-filled rear door which can be opened to expose the entire rear tube sheet and then the tubes affixed therein. Now, remember, in a fire tube boiler, the flame and the hot gases are contained within the tubes, and the water surrounds them, as indicated in the cutaway. With this dryback, you can also swing the front door to have full access to the front tube sheet as well. All of this for inspection and tube and furnace repair if necessary. Refer, if you would, to the image in the right-hand corner while noting how the water surrounds the tubes and the furnace. This, by the way, is a depiction of a 4-pass fire tube boiler wherein the flame and hot gases make 4 distinct passes before exiting out the stack. We start with the furnace, which is the first pass, and understanding the burner has been designed to match the volume and length of the furnace to allow the flame to only extend about 2/3 of the way down it. From here, all you have is hot gases traversing through the respective tubes, convectively transferring their heat before exiting. Baffles, as indicated with the red arrows, both refractory and steel, form the divisions, channeling the flow between the passes. The other horizontal fire tube is referred to as a wetback because of the water leg found between the turnaround plate and the rear tube sheet. This eliminates the heavy refractory rear door found in the dryback and replaces it with a much smaller refractory-filled plug or access way seen in the pictures on the screen. You'll also notice the wetback has 3 separate tube sheets, one in the front, one about 3/4 of the way down the boiler's vessel, and one at the end. Note the arrows pointing to each. We also see that the wetback is either a 3-pass or a 4-pass design. The large cross-section depicts a 3-pass, as denoted by the numbers indicating each gas passage, which is completed before exiting the outlet in the rear of the boiler. The water leg indicated on the screen, which is formed between the turnaround plate at the second pass and the rear tube sheet, provides the heat insulation requirement for the boiler itself. And this is the reason for the name wetback. Now, as far as advantages and disadvantages for each design, basically, the dryback has the distinct advantage of providing easy accessibility to the rear tube sheet, revealing all the passes of which the second pass is the most critical in any fire tube boiler, be it a wetback or a dryback. Now, with the wetback, as you can see, access to the second pass is very confined, and the space very difficult to work in when inspecting or repairing. The main advantage of the wetback, of course, is the elimination of the heavy rear refractory-filled door found on the dryback, which is sometimes cumbersome to open and reseal, and is an ongoing inspection and possible maintenance issue as well. The next fire tube boiler we will be focusing on today is the vertical fire tube, which typically has a smaller horsepower range as indicated, and fires either from the top down, or the burner can be mounted on the side of the boiler at the bottom. This picture, of course, is a top fire using a mantle-type burner firing into the furnace, and the hot gases then make one pass through the convection tubes using extended surfaces to greatly enhance the heat transfer coefficient, thereby affording excellent heat exchange before exiting through the flue gas outlet, which is at the bottom and indicated in the picture. These boilers are used in an array of commercial and industrial applications, especially where space is an issue. Commercial buildings such as apartments and laundries are prime examples of its application. The next major design categories we'll be addressing today is the water tube, which is indicated, is just the opposite from the fire tube, as the water is in the tubes and the fire and hot gases surround them. Now, many of the water tube boilers out in the market today have been designed to naturally circulate the water-steam combination through the tubes, utilizing properly sized tubes connected to drums or headers, providing the pressure density differentials required to naturally circulate. However, there are other water tube designs which require forced circulation, incorporating its own pump, and in a steam application, I like to refer to them as steam generators, and we'll be taking a look at these in a minute. Drilling down now into the various types of water tubes that you'll commonly find out there, we'll start with some of the smaller water tubes used in smaller commercial heating and industrial process applications. The straight inclined and the bent steel water tubes. Now, looking at the image on the lower left-hand side, you find the straight incline type using an atmospheric gas burner. But these can also be equipped with power burners burning oil, gas, or a combination. And then on the right, you see a bent water tube pressure vessel with all welded steel construction. Now, this is a steam boiler, which is also being used to heat hot water through a heat exchanger, which will be placed in the upper drum connection as indicated. Now, this might be for building heat possibly, or possibly domestic use such as sinks or showers. Also note the downcomers and riser tubes providing the natural circulation within the vessel. The sight port that you see indicated by the arrow is viewing inside the furnace. The next very popular commercial water tube boiler we'll be looking at today is the flex tube boiler, which uses serpentine tubes connected to the upper and lower headers and forming the various gas passes required to absorb the heat contents therein. Now, in this particular design, the hot gases make 5 distinct passes, including the first pass in the furnace, before exiting to the stack. This boiler was originally designed primarily for hot water comfort heating, as it was much more resilient to the possibility of thermal shock often encountered in these hot water systems. However, it was also found to be an excellent steam boiler and is applied in some process applications as well. It also has a distinct feature in that it has the ability to be readily field erected because the tubes are swedged into the respective headers, not requiring any welding. Now, here is the steam generator that I was referring to earlier. It's a vertical top-fired water tube boiler, but not a natural circulator as I have shown you so far. It requires a pump to circulate the water through the tubes and headers, and because of its very small water content, it can produce steam very quickly, but it's also very sensitive to water quality, as a design like this is susceptible to rapid scaling. Now, applications for this steam generator are primarily process, and because of its nominal size and output capacities, you often find multiple units which are sequenced through an integrated central control system and then stage fired based on the process load requirements, which we'll be talking about later, as I mentioned earlier. The next water tube type is the cast iron sectional boiler. Used exclusively for residential and commercial applications, this boiler is limited in design pressures due to the use of its castings, and is therefore never used for high-pressure steam applications. 15-pound steam is its maximum limit, and the hydrostatic limit is also reduced to this. I should say also reduced because of this. As you can note the limitations on the screen now. So it's a heating and very light process boiler with the advantage, similar to the flex tube boiler, of being field erectable. This means boiler retrofits are most often either cast iron or flex tube, especially in confined spaces which are difficult to access. Now, here is the copper fin boiler, which evolved primarily for pool heating, but is now used quite extensively for commercial building heat. You'll note the size range is small, but again, these are normally applied as multiple units with a control sequencer used to stage the firing based on system demand. The tube bundle is normally copper, but cupronickel is also available if water conditions might dictate, and the headers can be either cast iron or they can be bronze for the same reason. The copper fin units, similar to the steam generator, require forced circulation and normally employ an atmospheric gas-fired or fan-assisted burner. Now, the unit that I've got pictured here is referred to as a fan assist. Note also, these units cannot be used for steam, only hot water heating. Rounding out the water tube boilers we'll be looking at today is the industrial water tube, or what is commonly referred to as the IWT. These boilers are always built in accordance with Section 1 of the ASME Code, meaning they are always high pressure and used almost exclusively for industrial process applications. They're normally steam boilers, but you may also find high temperature hot water units as well, though they're not as common. Now, as you can see on the slide, the IWT comes in three common styles depending upon capacity and footprint requirements, and includes the D style, the O style, and the A style, which, as you can also see, incorporates three drums, an upper drum and two lower drums. And on balance, the A style offers the greatest overall capacity in terms of overall output. And speaking of output, these shippable packaged water tubes have capacities to 9,000 boiler horsepower. Remember, the fire tube I just described is 2,200 horsepower. And these industrial water tubes can go up to design pressures including 900 pounds, whereas the fire tube is about 250. You'll also note that these packages are fairly sizable. And though mostly are natural circulation, there are some IWTs which require forced circulation, especially when the heat flux or the ratio of steam to water in the tube, when those requirements call for inordinately quick steaming. Applications cover a wide gamut, from large central steam plants to large processing plants, including food, petrochemical, pharmaceutical, refining, pulp and paper, you name it. Now let's take a look at another type of popular boiler out there today, which really doesn't fall into the fire tube or water tube category. It's the vertical tubeless boiler. These boilers are mostly high pressure steam, but also offered in low pressure or hot water, and they can be found firing downward as depicted now on the screen, or they can be found with the burner mounted either on the side of the unit at about the midpoint or down lower at the bottom of the unit. In any case, they utilize a shell within a shell and multiple passes to absorb the heat from the combustion gases. Now, the unit on the screen fires down, as you can see. The gases then pass through the transition at the bottom of the furnace and then go across the outer convection zone covering 360 degrees, which is thinned to maximize heat transfer. Once passing over the convection zone, the gases exit through the vent connection at the top rear, which in this picture is not visible. Now, as noted, these vertical tubeless boilers have a limited horsepower range. Therefore, are again often sold in multiples with sequencing control and applied to various process and heating applications of a smaller scale. Let's say a small metal pickling operation would be a good example. The last boiler type we will be looking at today is the electric boiler, offered, I should say, in both the resistance and electrode designs. Looking at the slide on the screen now, you see the respective designs and how they break in terms of output, with resistance being between 12 and 33, almost 3,400 kW, and the electrode with a capacity between 2 and 65 megawatt. The resistance design has a series of electrical coils or bundles which allow the current to pass through, building heat as the current flows, and then heating the water surrounding them. In the case of the electrode boiler, the current passes directly through the water between the various electrodes, thereby heating the water directly as it flows from electrode to electrode. Now, as you can see on the screen, a kW is equal to 1,000 watts, and a megawatt is 1,000,000 watts. You'll also note a kW equals 3,413 BTU per hour. So if we are going to look at these electric boiler designs in terms of boiler horsepower, as we have with the other boilers that we've looked at so far, the resistance boiler ranges from approximately 1 to 350 boiler horsepower, and the electrode between 200 and 7,000 boiler horsepower. So these boilers cover quite a range in terms of capacity and uses, and are available for both high and low pressure steam or hot water, and an array of process or heating applications, with the main reasons for selection being on-site emission reduction, proximity to load, lack of fossil fuel availability, no stack requirement, like those buildings in Washington, D.C., and possibly low electric power rates, such as hydroelectric generation. Otherwise, these boilers are expensive to operate because of the cost per kWh when compared to a fossil fuel, even though the losses within and from the boiler itself are almost nil. So the application has to be right, but they're out there. So that pretty much covers what I was going to apprise you of with regard to the boiler categories, their typical types, their applications, and some of the design features. Now let's turn our attention, with the time that we have remaining, to an industrial steam application and the load to which these boilers may be connected. It's an extremely important consideration, and one which, if properly understood and engineered, can go a long way towards saving the finite resources of oil and gas and the dollars associated with the spend, in addition to improving the overall reliability and the overall cost of operation. You know, it all starts with the answers to the following basic questions, which will not only help lead to the proper selection of the boiler and the boiler type, but the correct capacity of the boiler as well. First, what is the total load the boiler will be encountering after the system is up to temperature and pressure? This will include all the connected users for process and heating. Then we need to decide on the pressure requirement, either for motive force and or the temperature requirement for the process or the heating application. Of course, you know, the higher the pressure, the higher the temperature of the heating medium. Next, we have what I like to refer to as cyclicality. This is the nature of the process. Will I encounter certain spikes during the day, such as a CIP requirement, clean in place, which will cause my steam demand to suddenly peak? Or maybe I have a food processing plant requiring fumigation, but it's only periodically throughout the course of the year. Or maybe I have a humidification load, but it's only in the winter months. These variations will cause my boiler to significantly vary its firing rate, and if not sized and engineered properly, will experience serious cycling problems and costing serious and needless fuel cost dollars. This then leads us to the possibly I should say, the most important piece of information we need to know about our system. What is my load the majority of the time? Where will the boiler's firing rate be during the majority of the day? So important to know in terms of what boiler size and burner turn down to choose to maximize overall fuel to steam efficiency. And lastly, we need to know if the process requires a minimum steam quality in order to mitigate system fouling while maximizing heat transfer. This refers to the amount of entrained water the process can tolerate within the system and within the steam. Okay, this water is entrained in the steam before we start to experience problems with the equipment or the process per se. So let's take a look at these points more specifically, and we'll start with the total load and pressure. Once we've determined what the total load is after the system is up to temperature and pressure, excuse me, we know, depending on the budget constraints, what we know, depending upon these budget constraints, if we need to go with one boiler or can we afford multiples. Remember, the package fire tube is limited to about 2,200 horsepower, and the IWT can go to approximately 9,000 horsepower in a single package. And as far as pressure is concerned, the fire tube tops out at approximately 250 pounds, whereas the water tube is about 900 pounds. So depending upon the capacity and the pressure requirement, the type of boiler choice may be decided right here. Next major consideration point is the cyclicality of my load. Will I have certain spikes in demand throughout the day? How much will they add to my normal load, and how fast will they occur? Will they be sudden or gradual builds? Is maintaining a certain steam pressure critical for the process during these spikes in demand? These are all very important questions to have answered before a particular boiler package is selected. For instance, let's say we have sudden steam demand spikes, and it's extremely critical that we don't lose pressure during these spikes. The fire tube boiler has some steam storage capacity in its shell, but once that's depleted, it's gone. And the pressure will begin to fall as it attempts to recover. Now, the water tube boiler, on the other hand, gives us a much faster recovery and is able to handle these sudden swings without losing pressure. So the water tube boiler may indeed be the best choice in this situation. Then there's the question of the burner's ability to turn down before the boiler cycles off, which of course will affect the load, both in terms of pounds of steam being delivered to the process, as well as the pressure. Normally, turn down is either a 4-to-1 or a 10-to-1, which means with a 4-to-1, a 100 horsepower boiler will cycle between 25 and 100 horsepower before cycling off when the demand drops below 25 horsepower. Now, the 10-to-1 burner will cycle all the way down to 10 horsepower before shutting off if the load drops below this point. The problem is that every time the burner cycles off, we not only lose output and pressure, but we lose valuable energy as well, because the burner needs to go through both pre- and post-purges for safety reasons, and this does nothing more than blow relatively cold ambient air across the boiler's heat transfer surfaces, robbing valuable energy as a result. And as a matter of fact, boilers which cycle inordinately, let's say 10 times an hour or more, can easily cost the customer 15 to 20% of their fuel bill per year in needless energy waste. So burner turn down becomes extremely important in meeting the process needs, as well as significantly impacting the fuel spend. The next critical point we want to consider in pertaining to load is, where is my load the majority of the time? This knowledge is critical in selecting the properly sized boiler once you have chosen the type that it would be, whether it be a fire tube or a water tube or some of the other boilers I just described. This because every boiler out there has what we like to refer to as its sweet spot, which may or may not be at high fire where boilers are rated in the catalogs. In other words, full output. And that efficiency is going to vary based on its firing rate. Let me show you what I mean. Looking at the curve on the screen now, it tells you a few things about this particular fire tube boiler. First of all, it gets pretty decent efficiency without any extra efficiency-related options such as an economizer. But it isn't at full fire. Notice how the efficiency drops off as the firing rate, which you see across the bottom horizontal, increases from about 60%, the highest efficiency point, to 100%. It drops off. Note also how the efficiency drops off rather dramatically as the burner turns down at about 60%. This means the sweet spot for this particular boiler is about 60% of its capacity. And if we are talking about a 200 horsepower boiler, for instance, this is a load of about 120 horsepower or 4,100 pounds per hour. Now, if that's what the normal load is, the majority of the time, 4,100 pounds per hour, this 200 horsepower would be an excellent choice, provided, obviously, that the other selection conditions are good as well. The other thing to keep in mind when considering cyclicality within the load is the time the boiler is going to spend at mid to low fire. And this is where the boiler's burner turn down plays a significant role. As you can see, notice how the excess air increases substantially as the burner turns down from 50%. This is a huge energy waster, not only because of the burner heating excess air, which is not delivered to the process, but because these low load conditions can often lead to excessive cycling as well. Now this could be a 4-to-1 or a 10-to-1 turned down burner. If that boiler hangs at that level, below 50%, you're losing a lot of energy. Now here's what I mean with regard to excess air and energy waste. When the burner on the boiler is set up in the field, the technician tries to achieve as close to 3% O2 or 15% excess air, they're synonymous, as he can without jeopardizing safety. So he's trying to hold that 3%. However, in most cases, when the burner turns down to the lower ranges, the O2 will climb because the damper can't seal off the air and allow only the required amount of air. And as you can see, for every 2% increase over the 3% ideal, you lose 1% efficiency. In the example shown, you see we went from 3% O2 to 7% O2, an increase of 4% O2, we lost 2%. Again, the best answers to the problem is to select a boiler with a mid-range or somewhat higher, as close to the majority of the load as possible, and one whose sweet spot is in that area as well. Or select a boiler burner package which is properly sized for the load and has a burner which can hold 3% O2 throughout its entire firing range or modulating range, be it 4-to-1 or 10-to-1. And those packages are out there. The other thing I wanted to mention here with respect to holding O2 levels as close to 3% as possible is the repeatability of the combustion control system and its ability to hold this level as the firing rate modulates throughout the course of the day or the weeks or the months. Now on the screen now you see two combustion control systems. The single point, including a single motor drive and a combination of linkages and rods, and then the parallel positioning system, which replaces the linkages and drives with programmable motorized actuators for controlling the fuel-air mix. Now, the single point system is used extensively throughout the industry and is fine if the burner doesn't modulate extensively. Now, if it does modulate a lot, the ball joints and the various nuts, bolts, and rods tend to loosen. They tend to wear and stretch, causing deflection and slippage, which results in air and fuel drift from the original set points. Whereas the motorized actuators hold precisely to the settings, repeating time after time throughout the modulating range and resulting in true energy savings year after year. When specifying a new boiler or a replacement upgrade, the combustion control system needs to be considered if you want to optimize the package. Returning now to optimum load matching, what I've been referring to so far is a single boiler being selected to meet the load, but also operate most of the time at its sweet spot when not handling various spikes. The problem is that some loads are so varied that one boiler cannot match the extremes while spending the majority of its time at its most efficient firing rate. The answer in this case is multiple boilers which not only provide redundancy, but can be selected so as to optimize their most efficient firing rates, calling for them to fire when the load demands and cycle down or off when the load dissipates. This is referred to as lead-lag control system, which intelligently stages the boilers to fire when needed and either allows them to fire only at the rate required to meet demand or fire in unison when online with the online boilers firing at the same rate to meet the demand. Again, whatever strategy is most efficient in terms of maximizing the sweet spot of all the connected boilers, which will have to be called into service at any given time. The other thing we often encounter in process applications where boiler is handling both process and comfort heating is the fact in the summertime, a considerable portion of the load is lost, and the oversized boiler cycles on and off extensively because of the loss of the heating load. It is here where we often find economic justification for what is often referred to as a summer boiler, which is now dedicated to and has been properly sized for the summer process, and thereby saving those extensive cycling costs and additional wear on the equipment. Certainly worth considering and going through the payback analysis. You may be pleasantly surprised. And as you can see, the boarder can come alone and tie into existing support equipment, or it can have its own skidded package, including a feed system and a softener if needed. The last major point one needs to consider when analyzing load is the steam quality requirement. The amount of moisture the steam can carry without affecting the process, as I mentioned. And it all starts with properly controlling various chemical properties in the feed water and the boiler water, such as alkalinity and suspended and dissolved solids, which can lead to foaming and carryover. And in most boilers, a proper chemical treatment and control program can result in steam quality between or being very close to 1.5% moisture. And this may be just fine, but if it isn't, then we have to look at other supplemental means, such as a more precise feed water control scheme, incorporating 3 distinct process variables, including not only level, but steam flow and feed water flow. Now, a system like this will greatly reduce the amount of sink or swell in the drum or shell and greatly reduce any carryover as a result. Next, we may have to consider other means, such as drum internals, as standardly found in the industrial water tube boilers, wherein the steam released from the generating tubes must go through a series of baffles, which essentially knock the water droplets from the steam and allow the purified steam to exit the nozzle. And as you can see, this can result in moisture separation to as low as 0.5%, pretty dry steam. Or we may be dealing with a fire tube boiler application, wherein placement of extensive drum internals are just not possible because of the restricted steam disengaging area not allowing access for inspection or repair. So in this case, we would recommend specifying an external steam separator, properly sized and placed in the steam header piping, as you can see on the screen now. Now, these are normally designed to use the centrifugal force of the steam entering the chamber, causing a spinning action within the body of the separator, and then throwing the water droplets out where they are channeled to its drain, and of course they're trapped and sent to the condensate return system. So that about covers it for today as far as the basics of boiler design and then the essentials required for applying these boilers to the process of the heating load. And I would say that your takeaways from today's session, at least from my perspective, would include the following. That boilers are constructed per the ASME code sections 1 and sections 4. 1 is high pressure, 4 is low pressure hot water. And also remember that in section 1, that could also be high temperature hot water. The boiler package consists of a pressure vessel, a burner, and controls, and also the controls are the burner management system, which is the flame safeguarder of the programmer, and then the combustion control system. All packaged together, single source, single responsibility by the manufacturer. There's various types of fire tubes and water tubes. We have a fire tube package limit of 2,200 horsepower and about 250-pound design pressure. Water tube packages to 9,000 horsepower and 900-pound design pressure. The water tube boiler is normally superior in handling the swing loads, as I went through an example before. Cast iron boilers, remember this, are low pressure and hot water only, not high pressure steam. Copper boilers are hot water only, no steam at all. And when considering the total load, look for the cyclicality spikes. Know where the load is the majority of the time, assuring the spikes can be handled within the boiler's turn down. Those are your takeaways. Now let's have some questions.
Thank you very much, Steve. While we're waiting on everyone to submit their questions, and if you would too, please submit them using the Q&A tool located on your WebEx control panel. if you do happen to use the chat feature, it may just take a little while to get to your question. So if you can, use the Q&A tool. If you have difficulty there, you may use the chat, but it may be just a little bit before we can get to the chat feature. Questions are starting to come in, but I did want to let everybody know that we do have 3 winners for locating the boiler icon, and I'll go to that page right now so everyone can see. But it was located on slide number 29. Taylor, do you have our 3 winners? They are the recipients of each will receive one $15 gift card to the CB store. And when we send out the gift card, we'll